Welcome to The Explainer. Today, we're peeling back the layers on a technology you use every single day, but maybe don't truly know. I'm talking about GPS, and we're going to dig into the mind-blowing science that powers that little blue dot on your map.
Okay, so let's just get right into it. You pull up a map, and there it is, that little blue dot that tells you exactly where you are. It feels like magic, right? But seriously, how does your phone pinpoint your location with such crazy accuracy just from some satellites orbiting, 20,000 kilometers up in space?
Well, it's not exactly magic. Think of it more like a massive, high-stakes game of Marco Polo being played on a cosmic scale.
So, first things first, let's get a key term right. You might hear people say triangulation, but that's not quite it. Triangulation uses angles. What GPS actually uses is called trilateration, and that is all about measuring distances from known points. And in our case, those known points are, of course, the satellites.
Okay, so here's how that works. Imagine you get a signal from one satellite. It knows how far away you are, but not in what direction. So that puts you somewhere on the surface of a giant imaginary sphere. Now, add a second satellite. Where those two spheres overlap, that narrows you down to a perfect circle. Pretty cool, right? But we're not there yet. Bring in a third satellite, and its sphere cuts that circle down to just two possible points. And, since one of those points is usually floating out in the middle of space, your phone has a pretty easy job figuring out which one is you.
But that just leads to the real question, doesn't it? How on earth does this little device in your pocket measure those mind-boggling distances with such incredible precision?
All right, get ready for the first big reveal. The secret to GPS isn't really about measuring distance at all. Nope, it's about measuring something way more fundamental.
Because here's the thing, the system doesn't measure distance. It measures time. Your phone is basically a stopwatch. It calculates how long it took a radio signal, traveling at the speed of light, to get from the satellite to you. Distance equals speed times time. The math is simple, but for it to work, the timing has to be, insanely, almost impossibly precise.
And that's where these come in. Every GPS satellite is carrying multiple atomic clocks. We're talking about clocks so ridiculously stable, they might lose a single second in, 300 million years. They actually define what a second is by counting the vibrations of a cesium atom. And that little atom vibrates over 9 billion times a second. That's the bedrock of the whole system's precision.
Okay, but all this incredible precision creates a massive, seemingly impossible paradox. And that paradox is sitting right there in the palm of your hand.
So here's the puzzle, right? The satellite has an atomic clock that's accurate to a few nanoseconds. But your phone, it's got a cheap little quartz clock that's just terrible by comparison. It loses seconds a day. It's kind of like trying to time an Olympic sprinter with a grandfather clock. How can that possibly work?
And this is a huge problem. If your phone's clock is off by just 1/1,000,000th of a second, your location is suddenly wrong by almost 300 meters. That's the length of 3 football fields. It seems like a total deal breaker, a fatal flaw in the system. So, how did the designers get around it? Well, this is where the real genius of the system comes in. It's all about a fourth satellite. Remember how we only needed 3 to find our 2 points? Well, that fourth signal isn't really for finding your location. No, it's there to solve for time.
Think about it like this. It's a simple algebra problem. You've got 4 unknowns, your location in 3D space, that's X, Y, and Z, and the fourth unknown is your phone's own crappy clock error. If you have 4 equations from 4 satellites, you can solve for all 4 unknowns. That fourth measurement lets your phone figure out exactly how wrong its own clock is, and then correct for it on the fly. It basically syncs your cheap little clock with an atomic clock in space. It's brilliant.
Okay, so we've solved the clock problem. We're golden, right? Wrong. Even with all of this, the entire system would completely fall apart in minutes. And the reason why is something that literally bends space and time itself. Einstein's theory of relativity. This is wild. There are actually 2 parts of relativity fighting each other up there. First, you've got special relativity. The satellites are moving incredibly fast, about 14,000 kilometers an hour. And because of that speed, their clocks actually tick a little bit slower than ours, by about 7 microseconds a day. But then you have general relativity. Because the satellites are so high up, they're in weaker gravity, and that makes their clocks tick faster than ours, by about 45 microseconds a day. So you've got one effect slowing time down, and another speeding it up. Turns out the gravity effect is stronger.
You do the math, and the net result is that the clocks on those GPS satellites run about 38 microseconds faster every single day compared to us down here on Earth.
Now, 38 microseconds, that sounds like nothing, right? But for a system that lives and dies by nanosecond accuracy, it's an absolute catastrophe. If the system didn't constantly correct for Einstein's theories, the location error would grow by more than 10 kilometers every single day. After just one day, it would tell you you're in the next town over. It would be totally, completely useless.
So think about that. This whole incredible system relies on quantum mechanics for the clocks and Einstein's relativity just to stay accurate. It's pretty clear it wasn't just invented so you could find the nearest coffee shop. In fact, its most important job is one you probably never even see.
That ultra-precise time signal from GPS is the silent heartbeat of modern life. It's the invisible scaffolding that holds up so much of our world. We're talking about synchronizing global financial markets down to the millisecond, keeping our electrical grids from collapsing, making sure our cell phones can hand off calls between towers. It's even used for scientific research like detecting earthquakes. It is everywhere.
And while the American GPS system really got the ball rolling, it's definitely not the only game in town anymore. The sky is now packed with navigation satellites from countries all over the world.
In fact, the proper term for the whole thing is GNSS, which stands for Global Navigation Satellite System. GPS is technically just the American system's name. It's kind of become a generic brand name, like calling all tissues Kleenex or all bandages Band-Aids.
So you've got the US has GPS, Europe has Galileo, Russia has GLONASS, and China has Beidou. The cool part is, the receiver in your phone isn't just listening to one system, it's listening to all of them at the same time. And having more satellites to talk to just makes everything better, more accurate, faster to get a lock, and way more reliable.
When you step back, it's just an amazing story. This invisible utility, something that was born out of Cold War competition and is fundamentally shaped by Einstein's wild physics, has become this essential public tool that has totally rewired how our planet works.
I mean, this system transformed Earth. It's a true testament to human ingenuity. So it just leaves you with one big question, right? What happens when we take this technology to the moon?